let's go ahead and hit present on my end. Get the good old pointer up, and then share screen. And let's see, Google Chrome. That should be it. Okay. Hopefully you guys can see my see these sort of slides that I have here. I have the chat here as well. If you can't see anything, or if there are any technical issues or any questions, or if I'm going too fast, please don't feel afraid to go ahead and drop something in chat. So the objective of like today's meeting is to focus solely on the qubit. So if you have a singular qubit, what constitutes a qubit, as well as the things you can do to a qubit. So this is if you've looked at some of the prior workshops that we've hosted, this is a lot more information that's condensed into one workshop. But I've whittled out a lot of information that I reviewed from the last quarter that I thought were unnecessary or maybe a little extraneous for our purposes. So yeah, these are sort of our objectives today. And I always love to start with the Schrodinger equation. Now, for those of you that may have prior experience with quantum computing, a lot of existing resources have a tendency to omit this information because they believe it is, they intentionally abstract it away. But I think it's doing a disservice to people who are learning about the subject to ignore the Schrodinger equation, which is the backbone of quantum mechanics. So I'll go over solving it, and I put solving in quotation marks because obviously I don't expect you guys to, be able to solve, second order partial differential equations off the top of your head, but to realize that the results of this equation are absolutely monumental and are the, once again, the backbone of quantum mechanics. And you also see that associated with this equation are operators and this idea of quantization, or discrete energy levels, and the fact that all the phenomena in our physical world that seems continuous and is not disrupted. There are no gaps. If we go to the quantum level, then you find out like it really isn't as smooth as you think it is. And then we get into how the qubit works. So that is sort of what we're trying to work towards today. So I'm going to start with the wave function here. So all quantum systems are defined by a wave function. And I want to point out that a quantum system, contrary to popular belief, does not have to just be a singular particle. If you guys are familiar with like buckyballs, that's the sort of colloquial term for them. They're, the actual term is Buckminster fullerenes. They're like a ball made out of 60 carbon atoms. So it's like multiple particles together. Atoms consist of other particles, but it's still, you can still define that through some kind of, it still constitutes a quantum system. So your wave function is not just restricted to a singular particle, although for the sake of convenience and mathematical analysis, we like to keep it at one particle, just for now. You'll see soon. And the idea behind this wave function, so we are approaching this function like a black box. I'm assuming that those in the audience may have not seen this function, so it's always good to just get a superficial idea of what it is. And we begin with our spatial coordinates. So you notice that we plug in some kind of spatial coordinate. So it could be Cartesian, polar, or spherical. So you can pick and choose whichever coordinate system works for you. And there's a time component as well, because these quantum systems are meant to, they don't just stay still in nature. They will evolve over time. So there's also this time feature. But for very simple examples, we just constrain it to one dimension. So like this picture here, I ripped this off a thumbnail for a YouTube video. But you'll notice that there's just X here. There isn't even a time component. And you'll see what exactly happens to the time component. I will explain why I have omitted that, but you'll notice we only have X here. So this wave function, this psi of X, is only in one dimension, just for purely for simplicity's sake. And the output of this wave function is a complex value. So it's got like a real component and an imaginary component, a plus bi. And this wave function is very useful to us because for any quantum system, that wave function encodes all the knowledge we want about that system. So the Hamiltonian, which is the sum of the potential and kinetic energies, the spin, momentum, angular momentum, etc. That could all be extracted from the wave function. But it's not immediately clear how you do this. So, but with a little elbow grease, with a little work, you can definitely get the information you want. And this picture kind of hints at it. You will note that even though the wave function is just psi of x, there's this additional stuff that's kind of dangling next to psi of x. That is sort of the secret sauce here. That's what really makes all this stuff work together. But that's the wave function. So it takes some Cartesian values, some component of time, and for our output we get some complex value. And that complex value, depending on a number of manipulations, encodes all the knowledge or all these physical observables. Observable is the actual term that we use in physics about the system. Now, we can't go crazy with our wave functions. There are a number of constraints that we should have. One of them is that the wave function has to be smooth. So what I mean by that is if you're familiar with some functions like 1 over 1 minus x squared, that's asymptotic. So it's discontinuous and there's like an asymptote in the middle. You can't have that as a wave function. You cannot have spikes or discontinuities. And furthermore, it has to be normalizable. And the intuition behind this is that if you take the wave function, so this time, I have the spatial and time components, and I take the sort of absolute value and square it, and I were to take the integral over this over a finite range. So I mean, in this picture, it's infinity to negative infinity, but instead I chose a finite range. You can get the probability that the particle is in some region or volume of space. So probabilities usually go from 0 to 1. So when we say normalizable, that means that if I add up all the probabilities of this particle, so I perform this operation here, it should all equal 1. Regardless of whatever wave function I choose, it will definitely all add up to 1. This is a constraint that we put on the wave function. And you'll notice that I say absolute value, although the reality is you're taking the conjugate of your wave function times itself. And if you know like complex numbers, this is essentially the equivalent to taking the absolute value and squaring it. So with that being said, let's go ahead and take a dive deeper into the wave. Oh, I should mention here absolute value. I mean, that's kind of it's more like it's probably arguable to say like amplitude or the sort of real component of your wave function, because this does, once you do this, your imaginary component kind of drops off the radar. So with that being said, okay, so the wave function in the Schrodinger equation. So this is the full-on Schrodinger equation. I mean, it looks very intimidating, but fret not. You won't have to worry about this too much in quantum computing. So the wave function doesn't live by itself. In every physicist's dream world, psi of x t would just be by itself, but it isn't. Because it's bound, you obtain your wave function through a second-order linear partial differential equation, and that's called the Schrodinger equation. Partial differential equation. So differential equation is just something that's in terms of its derivative, and then it's the partial. So you can have a function that takes multiple variables, in which case you have to deal with picking one of those variables and then performing your derivative analysis on it, or differential analysis. I'm going to skip the derivation for now. If you're interested, you can definitely look up how to derive the one-dimensional Schrodinger equation. It's a great exercise in physics, but I for the sake of simplicity and brevity, I am not putting it here. And we want to pay special attention to this particular term right here. It's u of x here, but in some physics literature they prefer v of x, and this is sort of the potential energy. It'll become clear in subsequent slides, but with that being said, we have our wave function here. It's stuck inside of this differential equation, and we're going to try and get it out. And once we extract it, you will find that there are a number of unique properties about that wave function. Oh, and this is a sort of a cleaner representation, and you'll notice that this is actually what the Schrodinger equation itself has all this stuff attached to it. The reality is it's like one term is the kinetic energy, and there's your potential energy, and then you have your total energy. And by tweaking, so for different particles or different quantum systems, you may have a different arrangement for your, especially your potential energies. then you will get different wave functions, which will reflect your different sort of quantum systems. And I think if you note with this one, this is different. I understand it's kind of off-putting because we're using R here, but that just means we're working in sort of polar coordinates or radial coordinates here. And this is meant more for this is a chemistry example. So in chemistry, you graduate from the one-dimensional representation into something spherical, I believe. Although I'm kind of interested in why this is missing some of the variables, but I digress. So there are some variants of the Schrodinger equation. One of them, so there's the time dependent and the time independent, and both of them are useful for different scenarios. So in the time dependent Schrodinger equation, we can see the time evolution of a system. So over time, your quantum system will undergo a natural order of change, and this is useful for certain modeling certain physical phenomena. But for our purposes, we only care about the time-independent Schrodinger equation, which makes it easier to obtain the energy eigenstates, or the energy levels of a system. And I have to say eigenstates, that's a mathematical term, but the basic idea is that the quantum systems have fixed energy levels that it can exist in. So if I have energy level of 1 and energy level of 2, the system can't exist in an energy level of 1.5. It's forbidden by the math itself. But for now, we'll focus on the independent equation. So one example of solving the Schrodinger equation is setting the potential energy to be 0. So if I go back, you will remember we have this u of x here. So I tell the equation like, okay, your u of x is 0 for a certain domain. And then so the potential energy is 0 for a certain domain, which is this well here. But outside of this domain, then you have infinite potential energy, which means essentially forbids the particle from ever existing in these realms. And with the potential energy set like this, this is just what we call like a boundary condition. So for any differential equation, especially partial differential equations, which model physical systems, you're always required to provide boundary conditions. So you notice like, okay, x equals 0, negative L over 2, and then positive L over 2 are just our sort of bounds here. And one of the results of doing this, like for solving for such a simple one-dimensional model, is that you get discretized energy levels. So if you notice E sub 1, E sub 2, E sub 3, E sub 4, the particle and its wave function can't exist in between. I can't have the particle at this energy level. I can't have it here. It's constrained to these whole energy levels. And you'll notice that you can't actually obtain an actual like a wave function here. And you'll notice that it is in the it's in the real domain. I mean, it's not giving you any imaginary numbers here, and that's just a part of working with the differential equation. Your answers for differential equations are functions, because you plug the functions back in and you do the derivative, and then it all pans out nicely. So this is the infinite square well potential, and this is for a system of one dimension. So this is just there are these discretized energy levels which arise naturally from the mathematical structure itself. So yeah, things to note, definitely you have those discrete energy levels, and this is where we get to those energy eigenvalues. So the idea behind an eigenvalue is, let's imagine that we have a wave function, and I'm applying some kind of transformation or some function to that wave function. What you're going to find out is, the equivalent, if I had a constant, like applying a constant factor to that wave function is just the same as applying this operator or other function to the to this wave function. So that specific integer value for E, given the Hamiltonian operator. So the Hamiltonian operator is responsible for deriving the total possible or the energy levels from the wave function. Will give you specific energy values, so like n equals 1, 2, 3, 4, 5, so on and so forth. So you notice that there's no continuous spectrum of energies. This is very counterintuitive to the real world, where I can, we can say like something's hot and it gets warmer and it feels like a continuous spectrum. But in reality, at the quantum level, there are only very specific allowed energies. So this slide will explain like this funky looking H with a little hat on it. And they're known as operators. So the Schrodinger equation itself has an additional built-in feature, And the built-in feature is an operator. That's part of the differential equation. The operators are applied to a wave function, and you obtain these eigenvalues, which are individual values that represent the value of. So the operators sort of, when you apply it to a function, you do that to extract information from the wave function, like what is the spin or the Hamiltonian or the kinetic energy. And when I say apply, it's okay. I can't say multiply, but you see like how this is a you can ignore this constant here, but you see like there's a partial derivative here. So if you just apply the partial derivative to a function, that would be considered an operator. And if you do your math correctly, you will come up with a discrete value. It's not going to be, and those, they'll have characterizable different levels, and yeah, those are your eigenstates or eigenvalues. So previously, the Hamiltonian operator was stuck on the Schrodinger equation. So if I go back here, you'll notice that, okay, this is the wave function here, but then you have a potential energy component, and then you have a kinetic energy component. So that's what I mean by the operator. It's actually supposed to be this plus, and then you distribute the wave function over to expand it out. But the Hamiltonian operator does consist of the potential energy, which you yourself can tweak for different quantum systems, and the kinetic energy. So that is, and that will give you the energy levels that your quantum system can exist in. And you can apply different operators to get different kinds of information. And we call this kind of information observables, because these are values that, we can observe as human beings. We're no longer dealing with some kind of imaginary wave function. It's a tangible result. So, our time-dependent Hamiltonians, kinetic energy. Okay, there you go. So that was, this is formatted kind of differently than I would like, but you still see there's your potential energy, and then there should be some kinetic energy component kind of dangling there. Now, with that being said, so this model, like the infinite square well potential, is just one very convenient example to work with, and where we set the potential energy to be 0 given a certain domain, and then we set these boundary conditions. But instead, one of the more useful models is the quantum harmonic oscillator. So we're still using the Schrodinger equation here, but we're tweaking how we represent the potential energy of that system. So with a quantum harmonic oscillator, there's a kind of restoring force acting on our system. So if it has a tendency, if it goes too much in one direction, there's a natural tendency to return to the original position. And the way I always think of this is, okay, like this little picture here. You can ignore the other diagrams for now. Is if I'm pulling this item away from that sphere, the spring will naturally want to pull that sphere back towards its rest position. So that's what I mean by a restoring force. And what's really neat or fun about these Schrodinger equation systems is you can start with a classical potential. So Hooke's law, which is used for representing systems with springs in the real world, it can be modified for the Schrodinger equation. So we just bring it down, or we transform it so that it works in the quantum mechanical realm. So you see that I think this is the original Hooke's law, and then we do a bit of I think we work with the you can put a transformation and get it into the this sort of potential energy that works with the Schrodinger equation. And okay, here's the actual picture of what the potential looks like. You'll notice that it's not like the square well. The square well was like, okay, you have infinite potential energy here and infinite potential energy there, and but instead it looks like this kind of parabolic shape. And you'll notice that the reason there are two overlaps is because the quantum harmonic oscillator is used very frequently in real world physics to represent, I think, the two atoms sort of near together, or at least two nuclei. And so you see that's why they say like internuclear separation. And you will still see your discrete energy levels that we saw this earlier with the energy eigenstates of the infinite potential well. And you'll notice that, okay, the green is an ideal harmonic oscillator. So if the potential was just this, but in the real world, things aren't as ideal. And you'll notice that the potential kind of skews to the right here, and it generally flattens out as you get to higher and higher energy levels. So the levels get closer and closer together as the internuclear separation kind of increases, at least according to this diagram. And the reason why I put this circuit here, if any of you have like, it's called a tank circuit or an LC circuit, because you have an inductor and a capacitor. This can generate or it can also be modeled as a harmonic oscillator. It produces a kind of a sinusoidal waveform. So it has a similar potential, I would argue. It's like a nice another analogy that you can think of, in that the current output from this will also be a sinusoid. So what's the deal with Hamiltonians? Like I've been focusing on the past few slides all on these Hamiltonians. Why do we care about Hamiltonians so much? What's so great about finding the energy levels of a quantum system? The great thing with Hamiltonians and that abstraction with operators and Schrodinger equations is that we don't really care how it's implemented. You'll notice that, I just said, oh, well, let's pretend the potential is a spring. I didn't say, it had to be, two nuclei or two atoms bonded together. As long as you, find it fit to use a certain potential, we only care about the energy landscape. That's what I always call it personally. Like if you look at a diagram like this is almost the energy landscape of our problem. We don't actually feed the Schrodinger equation, like the physical barrier. We represent our physical barriers or any physical constraints as a matter of choosing your potential energy. So we don't really care about the actual like physical environment. Like we can use the math to kind of abstract that away, or the physical thing at hand, which is why I mentioned like, oh, you have your Schrodinger equation and why it can work not only for one particle, but for systems of multiple particles, or like things that we would not inherently think are small enough to be quantum, to be subject to quantum mechanics. And that's where I get to the qubit. So the qubit, like the bit in our classical computers, is the smallest unit of quantum computation. Just as how like, okay, our computers might have 32 or 64 bits, and you use those multiple bits to do arithmetic operations and logic. Our quantum computers also have an equivalent, which is called qubit or quantum bit. And a quantum bit is considered at minimum, you need a 2-level quantum system. So I put here, you need 2 levels of something that can exhibit superposition and entanglement if there is more than one qubit. So these are superposition and entanglement are sort of 2 critical properties that are required. You'll see them in quantum mechanics, and you will need them in order to perform any useful sort of quantum computations. Now, what exactly is a 2-level quantum system? Well, if we go back to the harmonic oscillator, or if we even went back to the infinite square well potential, you'll notice that I have multiple energy levels here. So what they're saying by 2-level is that for a qubit, I only need 2 energy levels. But even more important than energy levels is realizing that energy is not the only 2-level thing in quantum mechanics. You'll notice how I mentioned with all these operators, we have the angular momentum and spin. Spin is another inherent property. I may attempt to explain that later on in the quarter as I try and teach you guys the different models of quantum computation and their physical implementations. But these operators will still give these sort of discrete eigenstates or eigenvalues, which constitute those quantum levels. So when they say like 2-level quantum system, those levels do not only have to be energy, they can be other quantum states as well. And furthermore, the constraint is that, okay, those quantum states should be subject to superposition, and they should also be subject to entanglement as well. I think in our first meeting, I went over these. So if you're not too familiar with that, I would strongly suggest checking out our prior meetings. And the neat thing that I keep emphasizing is the Schrodinger equation is not restricted to individual atoms or just singular particles, but larger macroscopic systems, is because qubits are not all done through singular atoms. It used to be in the early days, like you see this picture here. This is what we consider an ion trap. So it used to be that you could use ions, like individual ions, and you can manipulate their spin using a special sort of magnetic confinement system, and I think RF frequency radio waves to sort of encourage it to flip, somewhere in the order of gigahertz. But overall, as time progressed, there were other ways of implementing this 2-level quantum system, such as the superconducting silicon qubit. So there's like a picture here. I think this is like an implementation from Yale, if I'm not mistaken. But this is implemented in the same silicon that your computer that you're using to watch this Zoom call, or that you're using to text. you can also implement, and so the superconducting silicon systems use the energy levels. So with these trapped ions might prefer to use spin, I believe. But with superconducting silicon, you have discrete energy levels. And you can even use photons. So the photon polarization is another two-level quantum system you can use. And this is from another company, Xanadu. They also work with photonic quantum computing, although the two-level quantum system, that's the bare minimum. It's possible to have multi-level quantum systems. And if you're very much inclined, you can look up Q-trits. So, and that's like a three-level quantum system, or I think there's like qubits, like 4 levels, and you can do multiple levels, I think the multiple levels isn't what Xanadu's doing, but I just want to point out that 2 levels are the minimum, but you can go to higher levels. Although we have not, most implementations stick to 2 levels for the sake of simplicity. It's much easier to work with 2 levels, and it's just commonly accepted. 2 levels. There's like I guess with 2 levels, there's also a neat analog to our classical bits in computers, our ones and zeros. So last time, I don't know if is she here in our. I hope she's okay. I guess she isn't here. We had someone attend last time because I mentioned who asked a wonderful question, and I mentioned this idea of a Josephson junction. And a Josephson junction is used in the silicon superconducting qubits to attain those quantum mechanical properties necessary in silicon, or in a macroscopic silicon system like this fat, this large chip, to become a qubit. And the idea behind this Josephson junction is you can actually use, we begin with this tank circuit. It's implemented in silicon, and the Hamiltonian of this circuit is the arrangement is a quantum harmonic oscillator. So you see that the circuit here has the same Hamiltonian, or the same diagram as the thing that you would see here. So you see the LC circuit, or the tank circuit that I mentioned, without the Josephson junction. And I haven't mentioned what the junction is yet, but just give me a second here. So if I, just to refresh your memory, if I go back here, this is the harmonic oscillator, and you'll see that you have our discrete energy levels in this parabolic arrangement. And that is very similar. It's the same kind of system as you would see in this circuit with the inductor and a capacitor, which produces a kind of sinusoidal waveform. So a Josephson junction essentially, it's not a very hard concept or a device to physically realize. It's if I were to take 2 chunks of superconducting metal, and I put a very, very thin gap between them. The idea is that when superconductors operate on the principle that at a certain critical temperature, if I take a metal and I cool it, and I mean really cool it, like almost zero Kelvin, there is literally no electrical resistance in that metal. So if I were to put an electrical current on it, that current might still stay within the superconductor, and it allows for very efficient transmission of electricity. But there's another phenomena where at such low temperatures, electrons and electrons have a negative charge. So we normally think that electrons are repulsive, which is correct. But at such low temperatures, they kind of start to couple together. So those electrons start to have an attractive force towards each other. And by having 2 pieces of superconducting metal, and you put a barrier, it's possible to, I believe, from my memory, I might be wrong on this, the electrons can tunnel through that barrier. And you can use that Josephson junction to manipulate the harmonic oscillator landscape. So notice how in the original tank circuit, our oscillator here is evenly spaced. These energy levels are evenly spaced. But if I put a Josephson junction, our 2 levels are still, evenly spaced, but the upper levels are pushed away. And this is perfect, because one of the greatest nuisances in quantum computing, one of the biggest struggles in quantum computing, is avoiding noise. With these, energy levels, it's still a quantum system. Those energy levels are still really close together. And it's very possible that, a stray magnetic field or some spurious interference in the environment can cause your energy level to randomly jump up. So if I, push these other unwanted energy levels up further, then it's we have much more reliable two-level system to work with. So it's almost like, if you have a kid, and the stereotype that the kid's trying to get the cookie jar, and the cookie jar is on the kitchen counter, and with energy levels like these, the kid can easily get the cookies, which you don't want. That's an undesired effect. So we literally, using this Josephson junction, we're going to push the cookies to a higher energy level so that you can't, the system cannot possibly reach them unless we have an even worse amount of interference, in which case you might want to consider stronger shielding or error correction protocols. But yeah, that's what a Josephson junction does. It essentially allows us to custom tune our Hamiltonians, which is excellent for quantum computing. So before I can really jump into the glorious sort of math behind the qubit, I got to get this idea of Hilbert space to you. And most introductions to quantum computing, they would omit a lot of what I've just shown you. But I want to start you guys from the ground up and really give you the big picture before we dive in here. And Hilbert space is, I think, one of those things that is undeniable to your success in learning about quantum computing. So when we talked about the wave functions, these wave functions are nice. Like if we were hardcore physicists, pure physicists, we'd be dealing with wave functions for days. I could come up with all kinds of trivial potential energies, and we could spend our whole lives just trying to come up with these different energy landscapes. But the reality is, for quantum computing and for the majority of quantum physicists, it is a complete pain in the butt to have to deal with these, partial differential equations all the time. And so as a result, we're going to take advantage of an idea from linear algebra. And this idea from linear algebra is known as a vector space. So, as I mentioned, we exploit linear algebra. And the idea behind a vector space is you have a set of things with a specific set of well-known and well-defined operations. So we call it a vector space because traditionally you use it with vectors. And some of the rules here, like commutativity and associativity. So if I had like two vectors and you're adding them with parentheses and you change the order of the parentheses, you should still get the same result. Or if I scale a vector by a constant, and that vector should still remain in the space. Those are the kinds of well-defined rules that you will find in a vector space. But I want to encourage you guys to take one extra leap forward, another monumental leap, and understand that a vector space does not necessarily need to constitute vectors. You can use polynomials, and you have your own polynomial space as long as it has but there's some criteria to what constitutes a legitimate vector space. If you are really curious, you can check out the Quantum Computing Codex, which is it's sort of a introductory text that I've written. It's hosted online. I can put the URL in before this meeting ends, along with our prior meetings, which will give a more rigorous mathematical proof as to what this is. But the idea behind having or using vector spaces is now I take my wave function, I take those operators, all this stuff that we were working with in the quantum mechanical realm, as differential equations, and I can convert them into vectors, into this linear algebra terminology, which is much easier to work with, especially, and is much more scalable because you've heard in the news, like we're approaching tens, hundreds, thousands, and there's like one company out there, PsiQuantum, promising 1 million qubits. So and if you try and think about working with a differential equation that has like trying to represent millions of qubits, that's quite frankly impossible. In fact, one of the original purposes or goals of quantum computing was to be able to simulate those quantum systems much better. That was Richard Feynman's idea, like what better way to simulate a quantum system than to use a quantum system? So yeah, that's why. But I digress. It's just a super cool origin story. But that is why we use, or we like to use this idea of vector spaces, because now all of these wave functions and those operators with those partial differentials, we don't have to worry about them anymore. They're vectors now. So we are in the realm of linear algebra. So that's so we're just taking everything and we put it, and it's called Hilbert space. I mean, there are variants. So there's like finite and infinite dimensional Hilbert space, and this has to do with your basis vectors. So you know, in a linear algebra, if I have a certain vector, I'm supposed to be able to have two. I can take two perpendicular or orthogonal vectors and generate a third vector. So there's some, from that principle, there is, you can have either a finite or an infinite number of those basis vectors. So they're like two variants of Hilbert space. But you don't have to, you yourself don't have to concern yourself too much with the distinction yet. So we have, so our energy levels and our quantum states get represented as kets, which are part of the Dirac notation. Dirac notation is a really nice way of working with a lot of the stuff that you see in quantum computing. It had its start purely in quantum mechanics, but it is easy to extrapolate to what we see in quantum computing. You'll also notice, I wanted to briefly go over the idea of the Bloch sphere. And it's a visual representation of a single qubit state. And I want to get this through to you, a single qubit state. So if I have a system with 2 qubits or 3 qubits or n qubits, I can't use the Bloch sphere anymore. But the Bloch sphere is really cool in that, one qubit can be represented by a vector, and the vector has certain properties such as this, how much it leans from one sort of level to another, like this ket 0 and ket 1. Those would be considered like your two energy levels in your 2-level system. And then you also have a phase, because you still remember, like, wave functions in quantum mechanics can have phase. And phase is a very important, and I will admit it's poorly introduced in many other resources. So I will do my best to make sure that you guys have a very strong understanding of how phase comes into working with qubits. And but you'll notice that you can represent a qubit state as a vector. So if this visual representation is a really nice way of remembering this idea of the Hilbert space, that we are mapping everything through terms of linear algebra, and that makes our calculations exponentially easier to work with. So now we can, I might try and get into superposition and gates. So I put, this is a note for myself, but it's also an encouragement to you guys as well to see the notebooks. And I think I have a OneNote demo. Oh, that must have been when I was working on this as a draft. Oh, and of course the citations here. But I have a number of pre-existing graphics or resources that are designed to help you guys understand how the Bloch sphere works, as well as what I mean by stuff in linear algebra. So we have the basis kets, as well as your gates here. So I'm going to go ahead and start with our kets. Hopefully, you guys, I'm assuming you guys can still see my screen. I just got out of the PowerPoint. Let me go ahead and zoom in on this just to make things easier, and I will improve my lighting here, seeing as how it's almost 6 o'clock. So this, this is part of the Dirac notation. Unfortunately, I didn't put in the latex or LaTeX for the actual symbols, but you should still be able to understand what I'm pointing at here. So I mentioned earlier that we're working with a 2-level quantum system. So the way we represent our different levels, so we traditionally like to use, like, okay, one of them is like sort of is level 0 and then level 1, is that we use this sort of vertical, this column vector. And I'm using NP Quantum. NP Quantum is my sort of teaching library where I try and use Python to show you guys what's really going on here. And if I take this vector, a ket 0, and I plot it on our Bloch sphere, you'll notice, like, okay, it points vertically up. So that's telling us that our qubit is in its lowest possible energy state, because 0 is sort of your low energy, and then 1 is your high energy. And you'll notice that the abstraction here, I don't have to worry, is ket 0 energy levels, is ket 0 photon polarization, is ket 0 spin? That doesn't matter to us anymore, because we've abstracted it away using the Hilbert space and linear algebra. We can now, we're now free to play around with vectors. And ket 1 is 0, 1. So notice that, so the basis ket was 0, 1, and then, or ket 0 is 1, 0, excuse me, and then ket 1 is 0, 1. So 1, 0, 0, 1. These vectors are orthogonal to each other. And orthogonal is sort of, in my head, it's kind of a fancy mathematician way of saying perpendicular. And it can be kind of confusing because you'll notice that on the Bloch sphere here, 0 and 1 are in a straight line, which, in our intuitive sense should mean that no, they're not orthogonal, but that isn't the case. It's just that the visual representation may not necessarily show them to be orthogonal, but in all mathematical senses, they are. And if you want to know why this works in the Bloch sphere, I would encourage you to check out the quantum computing Stack Overflow. There's a much more excellent explanation than I can give you guys right now. But yes, that's so we have our basis vectors, 0 and 1. Now, it's possible to have this vector here, which is representing our qubit state, to not be like in line perfectly with 1 or 0, because 1 or 0 is still classical computing. In fact, we can have the vector point sideways. So what does it mean when it's pointing sideways? Well, it means you're in this kind of superposition between two states. So there's a 50% chance that when I observe or I interfere with this system, that I will be in 0, and there's a 50% chance that I'll be in 1. And this is something that isn't quite detailed too well in my slides today, but I think in my prior meeting I did do this. Is that for a quantum system, it can assume a multiple states, or it can be in this mixture of states until you observe it. And by observing, a lot of people get that confused because they think that, okay, observing means the particle is somehow sentient, and by looking at it, it knows that I'm looking at it, and therefore it will change. And that's not actually what's happening. The reality is, with any quantum system, the only way we can do an observation is to interfere with that system. So just like how in, I think, radar, for example, if I'm in my plane, I might not be able to see outside my windows, but I want to tell the cloud cover or other planes, I have to send this radio signal out, and the radio signal will hit any other object and it'll bounce back. So I have to literally interfere with my surroundings. In the case of radar, it's pretty much minimal or non-existent. But you go to the quantum level and it becomes very existent. It's very relevant and very prominent because we have to sort of destroy the superposition state, and you're forced to assume either 0 or 1. So now we get to the idea of gates, and gates are how we manipulate our qubit. Now, I should, before I go any further, there are multiple models of quantum computation. The gate model is probably the most popular and most universal, but if you're curious, there's the adiabatic quantum computation, which is another method of doing quantum computing, because you're still using a two-level system. You still have entanglement and you still have superposition, but you are encoding your problem as a Hamiltonian. And by slowly changing your Hamiltonian from a trivial ground state to the problem Hamiltonian, you can find your solution as the minima of the problem Hamiltonian. But that is another model. It's not as widely accepted there. But I just want to put that in your minds that, like I'm choosing to teach the gate model first due to popularity, but later on in the quarter, I will introduce you to other models, such as that the adiabatic method, which I have done some considerable investigation in. But the idea with these gates is that a gate is represented as a matrix. So you remember that in the beginning, ket 0 was a vector. So we're just multiplying the vector by a matrix to get another vector, or we're manipulating our quantum state using this matrix. Now, one of the things I want to point out here is the analog. The analog to gates in quantum mechanics are operators. So remember how I had a Hamiltonian operator, I had a spin operator. Well, gates are quantum mechanical operators as well. You apply it to a quantum state and you get another one out, and that's or you get another piece of they will manipulate your quantum state as well. So the X gate, all that does, like these X, Y, and Z gates, they just rotate. So if you look at my Bloch sphere here, I have my x-axis, my y, and my z. So the X gate just turns at 180 and it just brings it down to 1. So this is almost like the NOT gate in traditional quantum computing, or traditional computing, I should say. So if we go from 0 to 1 and from 1 to 0. But if I was in any other state, like I don't have an example here, But if the vector was at like y, like it's pointing in the positive y direction, and I apply the x gate, it will rotate along this x-axis, and it'll be in the negative y direction. So that's another thing. So that's the x gate. And then you can automatically figure out what the y and z gates do, which is, they rotate along this sort of y-axis here. And like for this example here, I sort of complained it's kind of hard to see in the beginning a rotation along the y. So I think what I did was I chose this state. So I put the vector sideways now, so it's on positive x. And if we perform a rotation, then you'll find out that we rotate along y, and we're on the negative x side. So when we perform the quantum measurements, you'll find out that it's indistinguishable, this positive x and this negative x, because you're going to collapse into 0 or 1 either way. But you'll realize this all comes back, like, why is it a sphere? Why is a qubit a sphere and not just 1 or 0? Or why is a qubit, excuse me, why is a qubit not a circle, or not, is a sphere and not a circle? Because I could easily represent superposition as a circle, because if I had a circle and the circle has 0 and 1, then if I take my vector and I put the vector in between the circle, I say, oh, hey, it's 50-50, 0, 1. Or if I move the vector upwards on the circle, then we'll just say, oh, it's 75% 0 and maybe 25% 1. Like, those are your respective probabilities. But because of phase is a part of the quantum wave function, there's this additional dimension that gets added. And as a result, your qubit's vector can also have this sort of rotational capacity. And you won't be able to immediately detect what this rotation is by a normal measurement, but there are such tools like the quantum Fourier transform and many other manipulations that rely on using phase as an additional method of encoding information, which is one of the powers of the qubit is, like, for one qubit, you can store or represent a great deal of information. Granted, you can't access it like you would normally in a computer, but you can still do useful computations in this unknown quantum state. So the z gate is just a rotation along your z-axis, and these are different matrices. So you notice that this matrix is oh no, sorry, that's not the matrix. That's the ket there. So this Bloch sphere is defined using imaginary values or as well. So you have your real and imaginary component. And yeah, you see, like, to multiply or to affect a qubit state, I am just doing matrix multiplication here. So those are your x, y, and z gates. And I think, so your Hadamard is another very special gate. And the reason being is that the Hadamard will take you from 0 or 1, and it puts you into the superposition state. And before you mistake the Hadamard for a traditional rotational gate like x, y, and z, this actually is responsible for, the way I think of it is that it helps you bounce back from phase space. So the rotations on the sphere, which are not immediately apparent, the Hadamard can help you translate that to the circle. So it'll be either 0, it'll be represented by changing the probability that you'll be in 0 or 1. So that's what your Hadamard can do. And that's a very special gate. And then we have, of course, gates such as the R-phi gate, or R-phi, I mean, depending on how you prefer to pronounce it, that will rotate, a certain number of degrees or certain radians along a particular axis, like, the S gate or the square root of the Z gate. So we already saw the Z gate earlier. The Z gate is a full rotation around the Z axis. So the square root of Z is because, 2 applications of the S gate will bring you to Z. Now, these matrices have a number of properties. I think I'll save that for the next workshop, though. But there are several constraints on what is considered a valid quantum gate, part of which has to do with Hilbert space, but more importantly, there's some conservation rules that have to be obeyed. So yeah, I can put this notebook and our resources in the chat here. I'll go ahead and stop sharing. And I will open it up to questions because I feel like I've gone through a lot. This is definitely a lot more than I would have normally done in prior quarters, but that's because I'm hoping to introduce some more useful algorithms to you without skimping, without giving too much detail, like deriving the Schrodinger equation, which I think I didn't derive it, but I did like show a way more information than was necessary to solve it. But I digress. So I will leave the floor open for questions, and feel free to take your time. I should also give a thank you to.
Hey, I have a question.
Yeah, go ahead. Go ahead.
Is there like any resources for like quantum physics or quantum mechanics for beginners?
Research for beginner. I'm not too certain. There are plenty of resources. They're kind of scattered. Like part of the goal of like my work is to try and like make it friendly enough for beginners. Quantum mechanics for beginners. I can't think of like a
maybe like a dummies version or something.
Okay, I see what you mean. I haven't been too successful on that front. Usually, like I'll tell you what my strategy is. I'll have to go through maybe 4 or 5 different sources, and then I kind of whittle it all together. Like, hold on, if I go to the, let me see if I can find it. I will show you the. Let's see if the live copy. Nope. Okay. There's a book that I wouldn't call it a book. It's more of an introductory text, the Quantum Computing Codex, where I've tried to gather as much of those like for dummies resources as possible. So it seems to make sense. The Quantum Computing Codex at QK. Hopefully this will come up with something. Here we go. And then let's see if I can get this to work. Shoot. Okay. I'll have to, maybe we'll send the URL out later, but there was an introductory text, and that's my effort to try and break down all the formidable stuff. I understand where you're coming from. So
I also like posted my mail.
Yeah, we can add you to the mailing list.
No. I am on the mailing list. I just for the copy, maybe like you could mail me like a PDF or something.
Oh, it's hosted online. It's a link. So I'll have the link posted through the mailing list, and you can access it there.
Okay.
Yeah, but that's it's still a work in progress. So I do apologize for that, but it's it's hard to work on a literal guide or text, with a quarter system in full blow. But yeah, that's that's what I would like to see from an introductory text.
Got it.
Yeah, I hope that answers your question.
Yeah, makes sense.
It's just there are no, as far as I know, there are no particularly friendly guides. Everything else is like I have to scrap together bits and pieces to make it tangible, unfortunately. You'll see that too in the guide. Like once you see the link, I have all like loads of citations because I'm pulling from all sorts of different places in order to make this
okay, got it.
Yeah, I'm more concerned that you guys understand it rather than like me going on a limb and trying to come up with some novel way of doing things.
Yeah, you did a great job of explanation, though. Not gonna lie.
Oh, thank you.
It was fairly understandable.
Thank you. I'm very happy to hear that. I'm always trying to improve and make things better, and your feedback is always welcome. So I'm very happy to hear that things are all right.
What about research though? Like, how does that work?
So like research in quantum computing, or like what kind of research exactly are you getting at?
Mostly like in the field of artificial intelligence.
So you're in luck.
Which also, why?
Quantum. So in the realm of quantum computing, there's something called quantum machine learning, because quantum computers are inherently better and faster at solving some of the problems like gradient descent and optimization problems required for artificial intelligence. So if you, I would encourage you to investigate quantum machine learning. IBM and Xanadu, they have some existing work, yeah, they you should definitely check that out.
Got it.
Let's see. Yeah, but there is research in that field. That's an excellent question, though.
Thank you, man.
Yeah.
What about in Davis? I'm trying to get some like at least like beginner research experience.
Okay, in Davis, okay, there's no quantum machine learning here at Davis, as far as I know, but there is work in Samarth. There's work in like material sciences and quantum biology, right? Or am I mistaken? I think our president and our vice president can speak more to that.
Samarth, you can go first on this.
Yeah, for like, for beginners, not a whole lot of research in quantum, to be quite honest. I would say like the most for quantum machine learning, I would look at the I think they just started, but like there's the Quantum Open Source Foundation mentorship program. I'll send you the link for it now. The one of the founders, Amira, she like is one of the machine learning leads at IBM. And so I would say that she and that program is really good for like getting started at the beginner level in machine learning. On campus though, yeah, like the club itself, like we started a research project in biology back in April for looking into how we can better model biological molecules on quantum computers. And we're trying to follow that up in the next few months with the project on protein folding, which we're trying to get funded by IBM currently. So whenever that project becomes live, then I'll definitely for sure send out to everybody like the application page for that, so you guys can all apply and potentially join that project and get paid for working there. But yeah, in terms of the other research, I honestly feel like Miranda would probably know more about that because she has done some like research in there, but it's more on hardware side, right, Miranda? Not really on software. I haven't really seen any software people at Davis.
Yeah, the only I would say the only quantum computing research you're going to find here is based like it's going to be physics based and essentially like bio based. The hardware would be what I'm doing specifically. It's called color centers like quantum research. So in this case, it's dealing with like the band gaps in certain materials, and then when you excite those types of materials, what type of photon, like what's the wavelength of the photon when it's released, and then you can detect a couple properties with that. But so far, I think that there's like quantum photonics research, and then a lot of research on the physics side, a lot of research in math for quantum, but that's getting into the more PhD style, like post-grad stuff right there.
Got it.
Wait a minute.
Thank you.
Link to QMAP real quick before you leave. I can just post that. That's for UC Davis.
Got it.
I'll once this meeting concludes, I'll have the recording up on the website. I mean, it's technically it's a subdomain of my personal website, but we're hoping that sooner or later this club will get its own home, and then I can migrate all the stuff there. But yeah, we'll have the resources all in one place. You should get it through the mailing list. And if there are no more questions, I think I might go ahead and conclude this meeting. But yeah, thank you so much for asking such wonderful questions and coming. It's always much appreciated. I always enjoy being able to teach new people and get them to really understand what makes quantum computing such an interesting and wonderful field to be in, especially in this current decade and upcoming decades.
Mhm.
Thank you for coming. Yeah,
You're welcome. Hope you have a good one.
you too.
Thanks,
Yeah.
everyone. See ya. Keep doing cool quantum stuff.
All right. All right, guys. Well, hope you all have a great rest of your week. Hopefully, if the schedule normalizes, I think the meeting should go back to Fridays. I know that's way easier for most people, and should have a better degree of attendance. Yeah. So, all right. Well, I'll see you all later.
For sure.
Yeah.
Sounds good. See you, everyone.